Bismillahirrahmanirrahim. Assalamu alaikum dear students. I welcome you to the next session of the Linux lecture series. Today we are going to talk about a topic that is known as inter-process communication. Let's start playing. So how to share information between Unix processes. So there are three ways that I have described on this board. Let's suppose that we have two processes P1 and P2 and they want to communicate. Previously, one process used to create a file on the disk, write onto that file, and the other process reads that file. This procedure was very slow because it involved the disk writing. Later on, Unix introduced the idea of creating a buffer inside the kernel space, an object that can be read and written by processes. So a process reads or writes this buffer and the other process writes or reads from that buffer. So this was pretty fast, but even then required mode switching from the user mode to the kernel mode and switching back from the kernel mode to the user mode. So later on, another way was designed, that was the shared memory, in which there was no mode switch involved. One of the process creates a shared memory region within its address space and gives permission to the other process to read or write it, and both the processes reads and writes this space. So these are the three major techniques that were used at a very abstract level. Just to give you an overview, the IPC mechanism used in Linux are divided into three categories. The first is the communication, the second is the signals, and the third is the synchronization. We are more interested in the communication, which can further be subdivided into two categories. One is the data transfer and the other is the shared memory. The shared memory is basically the same mechanism that I have just said, that the two processes share the user address space between them. It can be implemented using System 5 shared memory API or the POSIX shared memory API. It can also be implemented using memory mapping, which is further divided into two categories: anonymous memory mapping or memory mapped file I/O. As far as the data transfer is concerned, it is further divided into two main categories. One is the transfer as byte stream, and the other is transferring data as messages. In the byte stream, we have again three categories: pipes, fifos, and stream sockets. And in message passing, we have System 5 message queues, POSIX message queues, and datagram sockets. Today, with the next 20 or 25 minutes, I will be dealing with the pipes and the fifos, which are known as the name pipes as well. As far as signals and synchronization is concerned, we will talk about them in some later session. So let's talk about pipes first. A Unix pipe is an IPC mechanism that can be used between related processes. By related processes, I mean they can be parent-child or can be sibling. And the processes which want to communicate using pipes must be executing on the same machine. Executing on same machine. History of pipes goes back to the third edition of Unix in 1973. On the shell, you can create pipes using the pipe symbol, and on both the sides of the pipe symbols you need to have a command. Diagrammatically, the command 1 is converted into a process, and instead of sending its output to std out, it writes its output to a kernel maintained buffer that is known as a pipe, and the command on the right side of the pipe, instead of reading its input from std in, it reads its input from the output end of the pipe. So the descriptor 1 of command 1 is connected to the input end of the pipe, and the descriptor 0 of the command 2, that is the input, is connected to the output end of the pipe. And this can be nested, of course. By nesting I means you can have a long chain of pipeline. And what are the maximum number of levels that you can use on the bash shell? You can find it out yourself and let me know inside the classroom in the next lecture. So let us try these on the shell. Let me move on to a shell now. Here is our shell moving. So let's suppose that I want to view the listing of the etc directory. So there are a lot of files and directories which are there in this directory. I just want to see them line by line or page by page. So what is the option I have? What I can do is I can, instead of sending the output to std out, I send the output to another file, let's suppose temp.txt. Then I use less program and read the contents of temp.txt. So these are the listing of the etc directory which is right in front of me. I can see that, and then after that I need to remove this file. So this is a 3-step procedure. First I need to write the output on a file, then I need to read that output, and then finally I need to remove that file that has been temporarily created. So let's see the power of pipes. I use a pipe in between here, and then I send it to the program less. So the output of ls program is put inside the pipe, and the less program reads its input from the output end of this pipe, and you see the same behavior. Let's see it on this. Let's suppose over here. That means that if I write down the command like this, ls etc and pipe to less program, so what happen is, this is the ls program writes its output to this pipe. This is the less program which reads its input from this pipe and send its output to std out. Remember, this is the user space and this is the kernel space. This IPC object, which is a pipe, is maintained by the kernel. So let's see some other options, some other examples on the shell. Let's suppose that I want to see how many lines are there in the man page of ls. So I can count, keep counting, and then I move on to the end of this file finally, and I see that there are 284 lines, and right now the cursor is of course at 269. So instead of doing something like this, what I do is I output the output of man command to a program whose name is, let's suppose, wc-l. So I straight away get the number of lines which are there in the man page of ls. Let us suppose that I just want that I need how many times the string ls has come in the man page of ls. Let me repeat. How many times the string ls has come in the man page of ls. One option is that I start this and I keep seeing one, this is one line, so this contains ls, 2, 3, then I keep moving like this and keep counting. So this is a tough job. So let's see how we can manage it on using a shell pipeline. So I do man ls, I use grep ls, and then I say wc-l. So that means there are 12 lines in the man page of ls which contains the string ls. So the output of man command has been given to the grep command, and the output of the grep command, which has grabbed the string ls from the output of the man command, is given to the wc command, which has given you the output of 12. So let's see another example. Let's suppose that I say ls-lt. So ls-lt basically displays the long listing of the current working directory, and t says that sorted with the modification time. So these are the files, and I just want to see the first, let's suppose, 5 files. I just don't want to see all the files. So I pipe it and say head, and to head I say let's suppose 5. Okay, I think I have to give a hyphen sign to, yes. So these are the first 5 lines. You see the first 5 lines. You see the power of pipe. Similarly, if I do something like this, let's suppose that I say find Can anybody tell me what this command is going to do? This is the find command which says find in the present working directory all the files whose type is regular file and give me the count. It says hyphen type. Okay, let me put a hyphen over here. This is an option. 89. So in the present working directory and their subdirectories, the files, regular files, are 89. I want to see the directories, let's suppose. Put a D over here. 31. I want to see, let's suppose, I want to see the character special files, or let's suppose to be sockets. Do I have sockets? Yes, I do have a socket as well. And we all know that F is for the regular file, D is for the directory, S is for the socket, P is for name pipe, C is for character special file, B is for block special files, and similarly L is for the links. In some future lecture we will learn creating these 7 different file types in Unix. But anyway, you have seen the power of pipes. Using pipes you can write down very complex commands you can perform very complex tasks in a very simple way. Let's suppose that I say ls-l tilde. So what this command will do is that it will display the long listing of files and directories in my home directory, in the currently logged in user home directory. Okay, let me write grep PUCIT. Now it will display only those files which have been created in October. You see, only those files which have been created in October. Let me do something like this: sort -n, numeric sort. -n means numeric sort, we have done it before, and -k2, let's suppose. The second column is the link count. It is going to sort it according to this column. This command says finally that sort the output given by the grep command numerically based on the field 2, and the field 2 is this field. You see, this over here is not sorted, while over here it is sorted. So let me repeat the description of this command. The first part, the ls command, is gonna display the long listing of the currently logged in user home directory. The grep command will just grep those lines containing OCT string in it, you see. And finally the sort command will sort the output numerically based on field 2. Okay, gentlemen, let's see another related command that is known as the T command. So what is the T command? It reads from standard input and writes to standard output and files. Reads from standard input and writes to standard output and files. Remember, it writes to two places, stdout and file or files, maybe. Let's see. I say T, it is reading from stdin. I say rauf, Arif, and I press Ctrl D. So if you give no arguments to T, it will read from stdin and display to stdout. Read from stdin and display to stdout. And once you press Ctrl D, that is the end of file character, it terminates. What if I say T new file? Okay, instead of doing this, I say F1, F2 and F3. I say rauf, Arif, and I press Ctrl D. So what is the difference between running T without any argument and running T with an argument of, let's suppose, one or more file names? Over here, T will create 3 files. Let me explain it over here. Okay, let me create another bold. Take white pen. So if I say T F1, F2, F3, so what it is going to do, the T program will look something like this. It will take its input from stdin. It will of course send it to stdout, but it will also send its output to these 3 files on the disk, to file F1, to file F2 and to file F3. So over here you can do cat F1, so it contains rauf and Arif. You can cat F2, you can cat F3. Remember, if any argument is passed to T, it takes it as a destination file. It do not read from any file. If you want T to read from a file, you need to do IO redirection. Like, let's suppose, okay, this is a big file. Let me use F1. Okay, I say T, read from F1, read from F1, and that is it. If you want T to read from my F1, you cannot do something like this. Over here, T is asking for input from stdin, and it will write to stdout as well as to this file. Fine. You can use T in between a pipeline chain. For example, let's suppose I say PS hyphen A. Okay, let me use a lot of processes. So I have a lot of processes. PS, we know PS is process status. These are a lot of processes which are being run. The foreground, background processes controlled by terminal and daemons as well. A lot of processes. So we want to see them line by line, so I can do something like this, so you can see properly. What I want to do is I want it to be written to a file as well. So I'm going to use T. Now what will happen is the PS output will go to this file as well and to the less program as well. This is the less program which is working, and now you can less processes.txt as well. Let me show you how this works over here. What I've done is I've done PS T to a file, let's suppose F1 over here, and then to ls or less. So PS is a program which is gonna write its output to the pipe, and then we have a T over here, a T program, and the T program is going to write to the pipe again, and this T program is also going to send its output to a file F1 on disk, and then the less program which will send its output to std out. So this is how this pipeline chain is represented diagrammatically. I hope this makes sense to you now. Fine. We can always mix down the IO redirection and the pipes. Let me give you an example on the board over here. Okay, I need to do this. Fine. So can anybody tell me what this command is doing? Well, of course, the CAD program is going to read f1.txt and give its output to the grep program, and the grep program is going to grep the string PUCIT from that output. And what about now? The CAD program will write its output to the pipe, and the grep program will grep PUCIT string, and instead of sending it to std out, it will send its output to a file f2.txt. So this will be written to a file on the hard disk, that is f2.txt. Hope it makes sense. Let me give you another example. Let's say that we have a command like I have a file friends.txt. So this command is going to sort friends.txt and display it on std out. This command is going to get that output from sort and grep only those lines containing sheikh in it and display it on std out. That means this overall command will display only those names which have the string sheikh in them, my friends who are sheikh. And if I want that this should be sent to the std out, or this should be written to a file as well, so I can use T over here, and I can say, let's suppose T sheikh friends, shfr. Suppose this is the name of that file. So you see, you can use pipes, you can use T's, IO redirection, you can combine them, and that is really very interesting. Okay, so we know a bit about pipes now. Gentlemen, after some time, probably in 1982, the named pipes were introduced by Unix. Named pipes. Also known as fifos. As I defined unnamed pipes or simple pipes, that they are used for communication between related processes executing on same machine. The named pipes can be used to communicate between related or unrelated processes. However, executing on the same machine. Here the concept is again quite simple. Here is the process P1 and here is the process P2. They both want to communicate. They are going to use a pipe here again. P1 is going to write in this pipe and P2 is going to read from this pipe. And remember, these pipes are unidirectional. This looks same like unnamed pipe, but over here there is a file that exists on the hard disk. This is a file, let's suppose F1. And the important point is that the type of this file F1 is not a regular file. This is a pipe or a named pipe and represented by P once you see the long listing of the files. And you can create a pipe using the mk-fifo or the mknode command. Let me do it on the shell. I say mk-fifo and let me name that fifo1. It already exists, okay. mk-fifo 542. You see, we have two fifos, 541 and 542, and the type of both these files are not regular files. You see a P over here in the first character of the 10 character string that represent a named pipe. For a regular file we have a dash and for a directory we have D. Okay, so that means this is a named pipe. Okay. So you know, we can read the contents of a file. Let's suppose there is a file A, B, C, D, E, F, and I do A, B, C, D, E, F. Since this file contains nothing, so the cat program returns. And if I do cat from a file whose name is 542, suppose, so the cat program does not return. It blocks. So what I want to highlight is, once you try to read an empty file, an empty regular file, the program does not block. But once you try to read a FIFO, a named pipe, the program blocks. Let me write to a file. So this is a string which I am going to write to a file. Let's suppose A, B, C, D, E, F. So the string is written to this file. You can see that. So let me write the same contents to our FIFO, 542. Oops, 54. The program blocks. The string is not written. So what I want to emphasize is that once you try to read or write a FIFO, the program which tries to read or write a FIFO, it blocks. Okay, right. So to keep things simple, let me move on to a new directory. There is nothing in this directory. Let me create a FIFO using mknode this time. Previously I created it using mkFIFO. FIFO1, and I need to give another parameter to mknode command, that is a p, that is name pipe, because mknode can be used to create other types of files as well. You see, we have only one file whose name is this. Let me repeat the previous echo command. Learning Linux is fun, and let me redirect it to FIFO1. Let me move on to another terminal. Now you see, this is a FIFO1. The size of FIFO1 is 0 over here, and this is the echo program which is blocked on writing this FIFO. So the echo program is trying to write this string in FIFO, and on another terminal I am seeing that the size is 0 over here. So this is a writer program. Let me start a reader program over here. As soon as I press enter, I get the string over here, and this unblocks, and the size of the FIFO is still 0. So it's a bit confusing. Let's try and understand it on the board. Let me create another. So what has happened is that we have the echo program which tries to write a special type of file, a named file whose name is FIFO1. Once the echo program tries to write to this file, the kernel says, oh no, don't go to this file, this is a named pipe. Instead of going here, kernel creates a pipe and redirects the writing of the echo program to the right end of this pipe. That's why echo blocks. Echo is actually trying to write to this file, but its writing is going inside this pipe, and writing an empty pipe, named pipe, the writer program blocks. Now on the other terminal I started the cat program, and the cat program tries to read from this file, but the kernel redirects. The kernel says this is not a regular file, so instead of reading it from here, you read it from here. So data comes from here, and the data goes to the cat program, and of course the cat program displayed on stdout, and the echo programs unblocks. So dear students, remember, named pipe means a pipe with a name. Since this pipe has a name associated with it, therefore two unrelated processes can communicate using this name. The echo program is also using the name FIFO1, the cat program is also using the name FIFO1, and what the kernel is doing, it is creating a named pipe inside its memory, and it's redirecting the writing of the echo program and the reading of the cat program to this pipe instead of this actual file. So that means no data actually goes to this file, and that is the reason whenever you see the size of this file, you see a 0 over there. You will never see any number of characters or number of bytes written inside this file. So that is all, gentlemen, what I wanted to tell you today. Let me summarize again. What I started was the IPC mechanism, and I wanted to talk about the communication portion, and in the communication portion I talked about the data transfer portion, and in the data transfer portion I talked about the byte stream, that is transferring data byte by byte, and that I talked about the pipes and the fifos. The pipes are used on the shell using the simple pipe symbol, and the fifos, the name pipes, they are actually files which are created on the disk, and using their names two unrelated processes communicate with each other. That is all, gentlemen, what I wanted to tell you today regarding the inter-process communication mechanism used in Unix. There are a lot of details, and in the later part of the lectures or the sessions we will be talking about the other mechanisms that can be used between Unix processes for communication. I hope the lecture was informative. I wish you all the best. Happy learning. जहाँ का सबात है तुम ही से ऐ मुजा